Good morning, everyone. I'm going to introduce Joyce Kubrick, who will begin our presentations. Thank you.
Hello, everyone. It's really nice that you're able to make this switch right at the last moment. I'm sure you'll do a great job as you would have in person. But let me first introduce our guest speaker from Wallops Flight Facility, and that would be Victoria Dana. She is an educational specialist at Wallops Flight Facility. Go ahead.
Thank you so much, Joyce. Good morning. As Joyce said, I'm Victoria, an education specialist at Wallops Flight Facility for our Suborbital and Special Orbital Projects Directorate. And thank you so much for joining us today for the Space Coast Scholars final presentations and closing ceremony. Our partnership with Virginia Space Grant has truly been exceptional, and as a result, hundreds of students over the past 10 years have been able to learn about Wallops and NASA missions. The students you will see presenting this morning arrived on Saturday as strangers, and in less than a week's span of time, developed a NASA mission using one of our key launch platforms: small satellites, scientific balloons, sounding rockets, or expendable launch vehicles. Scholars, you are to be commended for your dedication not only to your participation in the program this past year, but also for your willingness to take time from your summer breaks to spend it as a Virginia Space Coast Scholar. Parents, your children performed brilliantly this week, taking on the challenge of designing a mission to fly on board one of NASA's premier science platforms. They explored their platforms, pitched ideas for science experiments, and eventually pulled together plausible and interesting missions to share with the NASA community. I would like to thank Virginia Space Grant Consortium and our Wallops subject matter experts for their support. Additionally, I would like to extend thanks to the Wallops education team, including Dr. Joyce Winterton, Pat Benner, and Linda Sherman. At this time, I'm going to pass the baton back over to Joyce Kubrick for the mission presentations. Thank you so much.
Okay, thank you, Victoria. So now we're going to proceed on with our mission presentations from our students. I would just like to say a few things first, give you a little overview of the program. So students have been working online since December. Well, no, November is when they started this year. And they finished their online course in right at the beginning of April, end of March. So during that time, they were working on 5 modules, and it was a lot of work. And I'm sure it was a lot of work considering that they actually had their schoolwork as well. But these students did exceptionally well, and that's why they're here today, because of their academic excellence in the online course. So since we've been here we were there at Wallops and UMES, the students were working together diligently. Even though we had that little COVID situation, the students was able to go on to Wallops and meet their mentors and work with them for a couple of days and see the facility. So I'm glad that they were able to do that. And they did extremely well and very resilient students. So we're going to go ahead and get started with their mission panel presentation. And our first group up will be the sounding rockets. So sounding rockets, go ahead and upload your presentation.
Hello all, I'm Caitlin Miller from Hamilton, Virginia, and I'm the program manager as well as the instrument specialist in the engineering office. Today we'll be introducing you to the dual investigation of ozone depletion in the environment mission, or DIODE for short. And this mission will be aimed at studying polar stratospheric clouds and the effects that they have on chlorine, nitrogen, and ozone concentrations within our atmosphere, particularly around the tropopause. Next slide, please. Well, although our DIODE mission is going to be managed by Wallops Flight Facility, it will actually be launched from the Poker Flats Research Range in Alaska. And it will be utilizing 2 main platforms. First of all, the 2-stage Black Brant 9, which is a sounding rocket, as well as our weather balloon to take more measurements.
Hi, my name is Samantha Ho. I'm from Fredericksburg, Virginia, and I'm a research scientist from the science office. So our NASA goal statement is to expand human knowledge through new scientific discoveries, and our NASA objectives are 1.1 to understand the Earth's environment and its climate, and 1.3 to ensure that NASA's science data is accessible to everyone and to produce practical benefits to society.
Hi, I'm Gabriel Ignacio from Berryville, Virginia. I'm a research scientist in the science office. Our science goal is to expand human knowledge on polar stratospheric clouds, which we intend on accomplishing through our science objectives, which are to figure out the compositions of ozone layers in the stratosphere and the troposphere, determine nitrogen and chlorine compounds concentrations. There are various compounds that we'll get to later. And to measure the temperature at the target altitudes, which may depend on where the clouds are. Some of the compounds which we'll be measuring are chlorine monoxide, hydrogen chloride, carbon tetrachloride, trichloroethane, trichloromethane, nitrous oxide, and various other trace gases, many of which are ozone depleting.
Next slide, please. Okay. So our sounding rocket is going to reach an altitude of about 175 kilometers. And then shortly after that, about 60 seconds, we're going to release a weather balloon, which will reach 15 to 20 kilometers.
Hi, my name is Charlotte Draney. I'm from Fredericksburg, Virginia, and I am the environmental scientist in the environmental office. The following timeline overview is in collaboration with the National Sounding Rockets Program Office out of Wallops Flight Facility and the Poker Flat Research Range near Fairbanks, Alaska. Our extended mission timeline, as outlined here, allows for about a 4-month mission collaboration and proposal phase, about a year for design, 11 months for testing and integration, and about 2 weeks for our launch period. Our timeline is structured around routine checks managed by the National Sounding Rockets Program Office to ensure that we guarantee a successful mission when it is time for launch. This is a closer look at our launch operations phase of our mission. Our phase begins once all of the materials and personnel have been transported from Wallops Flight Facility to the Poker Flat Research Range in Alaska. Weeks 1 through 3 include our reintegration and testing phase, where we will be preparing the balloon, setting up GSC, doing pressure tests, and charging our batteries after relocation. Weeks 4 and 5 is our actual launch window, where the scientists on board are going to be monitoring the weather around the clock to ensure that they launch the rocket when there are optimal observation conditions. Once our scientists have determined that the weather won't prevent the instruments from collecting the appropriate data, then they will launch the rocket, and then 60 seconds later, they will launch our balloon. During the time that our team will be in Alaska, we have to take considerable measures to ensure that they are protecting themselves, as well as the platform and its instruments. Because of the extreme cold temperatures, the sounding rocket will be encased in a styrofoam shell to protect it from the cold and prevent any damage. Additionally, the scientists themselves have to wear appropriate PPE to ensure their safety. And lastly, we have an agreement with the Poker Flat Research Range in Alaska, where any platform that we launch, we must recover to prevent any negative impact on our environment. However, this recovery won't occur until later in the year because it is a routine recovery process where all sounding rockets from all missions are going to be recovered.
Hello, my name is Miguel Halos Maza, and I am from Purcell, Virginia, and I am an applied scientist for the Science Office. The legal information is agreements between different departments that allows us to launch the rocket. The first department that we have an agreement with is the Arctic National Wildlife Refuge, which requires a sounding rocket to be recovered. The International Traffic in Arms Regulations requires the United States to control military-related technology and requires the Technical Assistance Agreement to be signed for international launches or collaborators. The space law is an agreement of laws in space between every country. One of the laws makes a country liable for damage caused by a spacecraft launched from the country. The Federal Aviation Administration establishes a no-fly zone in the rocket launch area and gives an early notice for pilots. The Commercial Space Launch Act requires a license to be obtained for any proposed rocket launch. The short-term economic impact includes meteorology. Our mission will affect the study of meteorology as it will impact the change of the atmosphere due to the depletion of the ozone layer. Constructing the mission can impact the Eastern Shore's economy because of the usage of items and land to construct the rocket. This mission will affect weather modeling as it will disturb the accuracy of the weather information in the atmosphere. As UV rays start to affect many people, many public policies will need to be changed so people can stay safe. Next slide, please. The long-term economic impact includes medical expenses. Higher exposure of UV lights will increase many health issues. Agricultural expenses will increase due to the few numbers of surviving crops in areas of higher exposure. As the ozone layer depletes, the UV rays will start harming plants that produce food, and a decrease in food production will slow economic growth for all countries. Without the ozone layer, there will be many natural disasters, such as tsunamis, major floods, and hurricanes that can damage many cities and buildings worldwide.
Hello, I am Olga Klinichenko from Reston, Virginia, and I'm an applied scientist in the science office. Our mission stakeholders include universities who will be able to use the collected data for further research. Additionally, we partner with the University of Alaska, who owns the Poker Flat Research Range. The scientific community would also benefit from our mission, as it would provide newer insights and knowledge of stratospheric clouds and their effects, which can be used for further research. Lastly, our stakeholders are some of the government departments, as they will be able to use our information to make decisions and conduct research within their areas of expertise. Some of the benefits of our mission include more information gathered on polar stratospheric clouds and their effects on the environment, more information on stratospheric and tropospheric ozone layers and their state. We will also collect data on the temperatures of polar stratospheric clouds, so that we will know at places with what temperature they usually appear. And lastly, we will study the effects of polar stratospheric clouds on the stratospheric and tropospheric ozone layers specifically.
Hello, my name is Edwin Kyle. I'm an instrument specialist from the engineering office, and the principal instrument we'll be using aboard the sounding rocket is the microwave limb sounder, or MLS. The MLS measures ozone and trace gas concentrations, the temperatures of those gases, and provides a vertical profile within 15 to 20 kilometers, which is our target range of altitude in which polar stratospheric clouds are most likely to form. Next slide. All right. We're going to be using a multi-wavelength IR camera also with a 8 to 15 micrometer wavelength, and it's going to create an overall temperature profile of the clouds below within the 15 to 20 kilometer range. And this information will help us know the areas where PSCs are more likely to occur, because they usually form below negative 78 degrees Celsius, which would be the purple area on this map on the right. So aboard our balloon, we're going to have the lightweight airborne chromatography experiment, or LACE instrument, which will take in situ gas concentration measurements within the polar stratospheric clouds. We're going to modify it to measure chlorine monoxide and hydrogen chloride concentrations to be consistent with the MLS instrument. And this is an image from the NASA Middle Stratosphere program, and the payload depicted included the LACE instrument, which is about 50 pounds. Next slide, please. Which is equipped with the Earth Observing System Microwave Limb Sounder instrument, which our MLS is based off of. It's also equipped with the Ozone Mapping Instrument, or OMI, which distinguishes smoke, dust, and sulfate aerosols. And it also maps ultraviolet B-type radiation. And we're going to use this information to confirm and validate our results from the sounding rocket and balloon.
As with any launches, there are many constraints, including the mass. Your average sounding rocket max payload weight capacity is around 900 kilograms. So currently our MLS instrument is in production to reduce its mass to reduce it by 25% to get the total diode payload weight of around 500 kilograms. And this will allow the sounding rocket to reach a maximum altitude of around 170 kilometers, which will give the instruments around 4.5 minutes of observation and data collection time.
Hello, my name is Lily Bowman. I'm from Virginia Beach, Virginia, and I'm a public relations specialist from the Office of Communications. We chose a blue gradient for our mission patch because we thought it was more visually appealing to the eye. In the center, you can see polar stratospheric clouds, which is what we will be studying on the mission, along with our mission acronym and the Black Brant 9 rocket, which is the rocket we'll be using for our mission. For public outreach, we will attend local events, visit schools, attend teacher workshops, and work with the National Science Teaching Association. For our lesson plan for K through 12th graders, our lesson will last 2 days. On the first day, we'll be teaching about sounding rocket history, and then specifically our mission. On the second day, students will be building a miniature sounding rocket that they can launch, and there will be a Kahoot quiz. We want our mission plan to be fun so students can be encouraged to research on their own time.
Hi, my name is Evan Huang. I'm from Chantilly, Virginia, and I'm a public relations specialist in the Office of Communications. For our education outreach, we have developed 2 different scholarship and internship opportunities. We have created these flyers to be distributed to teachers around the country. The first is an essay. The first opportunity is an essay competition with the essay topic of how does diode benefit the world and how does it help stop ozone depletion? The second flyer is an internship opportunity for people that want to contribute to diode directly and work with NASA professionals. Here's our website with more extensive information about our mission. We have a heavy social media presence on platforms such as Instagram, Facebook, and Twitter, where we regularly post updates about diode. Our goal with these social media platforms is to reach a wider audience and increase public involvement in our mission. Here is our press release, which includes an overview of our mission and goes over our purpose, impact, and methodology behind our experiment. And finally, we would like to thank everyone that has helped us through this mission and journey, including the Virginia Space Grant Consortium, Virginia Space Coast Scholars, and all the NASA specialists. Thank you for listening to our presentation.
Okay, so great job, sounding rocket. So what we'll do now is we'll see if anyone has any questions about their mission. Just type it in the chat and I will read off the questions. Okay. Questions. Why did you select poker plats?
That is a great question. Polar stratospheric clouds usually form around very low temperatures. So we chose Poker Flats because that's most likely where the polar stratospheric clouds will form, and we'll get better measurements with the weather balloon as well as the sounding rocket Black Brant.
Did that answer your question? Okay, excellent presentation. How many team members will need to be in Alaska for the launch of your mission?
We don't have an exact measurement for how many different members we will need. However, we'll need enough to launch the sounding rocket as well as the weather balloon. And then since we have the agreement, we have to collect all of the different parts of the sounding rocket that are launched in the summer, since we're launching in December. And then we will also need to get the weather balloon and styrofoam casing cleaned up.
Okay, great answer. Any more questions for the sounding rockets? Why is the school community outreach important for your program?
School community outreach is important for our program because we want to increase public involvement in this project in Diode. And one way to do this is by reaching out to schools and making sure that kids are educated about our mission and why it's important.
Okay, good. Nice job. Great. How do you plan to do outreach for those in the rural communities? You need me to read the question again? All right.
Yeah, so for outreach to rural communities, we plan to distribute flyers to teachers around the country, and we're also broadcasting through radio.
Okay, another question. Why is it useful to make this mission about PSCs than it would be to make the mission study noctilucent clouds? Why are PSCs worth studying more than NCs?
We haven't yet looked into noctilucent clouds. However, that will be on our radar in the near future. Currently, to our knowledge, we know that polar stratospheric clouds facilitate the depletion of stratospheric ozone, which is beneficial to us here on Earth, and it increases the concentration of tropospheric ozone, which is harmful. So by studying the polar stratospheric clouds, we can understand how they currently affect our ozone layers and us on Earth.
Okay, good answer. One last question. Have you considered noctilucent clouds? If so, would your mission be able to provide any insight into them?
Yes, so we haven't considered noctilucent clouds yet. However, that is going to be coming in the near future. So far, we just know that the polar stratospheric clouds help facilitate the depletion of stratospheric ozone and increase of tropospheric ozone. But we'll definitely be looking into the noctilucent clouds here in the near future.
Okay, great job, sounding rockets. So we're going to move on to our next group, which will be scientific balloons.
Hello everyone, my name is Lauren Pegger. I'm from Yorktown, Virginia, and I am the project manager as well as the environmental scientist from the environmental office.
Today we are presenting on our mission Rampart, which stands for Remote Analysis of Magnetic Microprotection for Avoiding Radiation Trauma. For our mission overview, we are going to be setting up a scientific balloon to test passive magnetic shielding to protect bacterial life from radiation. So we will be setting up 2 incubation chambers that both contain bacteria. One will have a magnet attached to see if that helps deflect the radiation. The reason for this mission is we are going to use this information to protect astronaut health for long-term spaceflight, as well as we can develop medical spin-offs for the general population.
Hi, I'm Meghna Krishnavarapu. I'm from Vienna, Virginia, and I'm a research scientist from the Science Office. And for our NASA Science Goals, we're looking to develop capabilities and perform research to help safeguard astronauts for future deep space missions, along with advancing mission support capabilities for the next era of aerospace, again, for extended deep space missions. So our first science goal for our mission is to investigate the effect of a magnetic field on radiation affecting a payload. So we're going to be measuring alpha and beta particles that come from solar winds, along with heavier particles that come from cosmic radiation when a payload is and isn't protected by a magnet, along with comparing local magnetic field strength, again, when a payload is and isn't protected by a magnet. Our second science goal is to analyze the harmful effects of radiation on bacteria. So we're going to be inferring the growth and death rate of bacteria, along with observing and measuring the density and growth rate of that bacteria over time.
Hello, I am Dalton Johan. I am from Salem, Virginia, and I am a research scientist for the Science Office. So for our mission stakeholders and planners, partners, there has been some preliminary research into using magnetic fields to deflect radiation. This has been done by Johns Hopkins and Rutherford. So these would be stakeholders in our mission because they would be interested in progressing their own research. Additionally, for our federal partners, we need to partner with NASA and Wallops Flight Facility in order to have the capability to put a scientific balloon in the air. Additionally, we need to partner with the National Science Foundation, who will help us get a payload to Antarctica. For our bacteria, we will be using Lactobacillus acidophilus. It is commonly found in dairy products, and it uses a pH of 5 and 30 degrees Celsius for optimal growth conditions. These are pretty easy conditions to meet in the upper atmosphere. The temperature is close to what is occurring in the upper atmosphere above Antarctica. Additionally, it duplicates every 1 to 2 hours, which means that in our mission time, we will collect a decent amount of data, but we will also not have the bacteria grow too much. The 30 degrees Celsius growth temperature means that when we drop the bacteria down into Antarctica, when we're done with the mission, they will go into stasis, which means that we can perform post-analysis, and that post-analysis will be a variation of the Amy's test.
Hi, I'm Carson Ray from Roanoke, Virginia, and I'm the instrument specialist from the engineering office. On our mission, we will have several instruments to compare the radiation affecting payloads with and without magnetic protection, including the energetic charged particle detector, which will measure the radiation from light particles from solar wind, cosmic ray spectrometer, which will measure the energy and type of heavier radiation from cosmic rays, and a fluxgate magnetometer, which will determine the magnitude and direction of local magnetic fields to compare the magnetic influence between the two payloads. We will also be using instruments to compare the bacterial growth with and without magnetic protection, to include optical turbidity spectrophotometer, which will measure the optical density of the total bacterial mass, and the infrared thermography camera, which will measure the metabolic heat production of only living bacteria. We also have several operational components essential to the success of our mission, including the passive magnetic shield, which is a rare earth neodymium magnet with a magnetic field strength of 1 Tesla. We'll also be using a dual payload cable extender system, which consists of a winch and 2 Kevlar cables that will lower the secondary magnet payload from the primary payload to separate the control group from the magnetic field during data collection. We also have incubation environment control system, which is a heated and insulated incubation chamber with the proper conditions for L-acidophilus growth. We have two main methods for data acquisition, including in-flight telemetry of critical science data from all the instruments over line of sight when the balloon is close and over the TDRS and Iridium satellite networks elsewhere. We also store all data on board the balloon for recovery after mission termination.
So as far as environmental impacts, scientific balloons are one of the lowest impact platforms because we don't create any emissions during the flight. We are also going to recover all of our entire payload as well as the entire balloon. This may take a few years because in Antarctica there's unforeseen weather, but all of it will be recovered. For a platform, we are going to be using a zero pressure scientific balloon with an area of 39 million cubic feet. It will fly at an altitude of around 130,000 feet, which is nearly 99% of the atmosphere. Our payload will weigh about 2,000 kilograms, and we will be launching from McMurdo Station, Antarctica. The flight duration will be around 6 or 7 days because this will get us roughly one circumnavigation of the South Pole during the time of launch, which will hopefully have recovery close to McMurdo Station. For our operations timeline, we will begin assembly of our instruments this year, and we will start testing them next year with balloon fabrication beginning then. In 2024, NASA requires all flights from Antarctica to have a test flight. So we will do a 24-hour test flight out of New Mexico roughly 1 year before. In 2025, we will revise anything that goes wrong during that test flight. Then in November, everyone, including the payload and the balloon, will travel to Antarctica. And in late December, we will begin our 7-day flight of the balloon. Then by 2027, we hope to have recovered everything by then and do all of our post-analysis tests.
Hello everyone, my name is Charlie Schmidt. I'm from Fairfax, Virginia. I'm an applied scientist from the Science Office. So in order to execute a mission of this magnitude, we must adhere to legal requirements of various organizations around the world. Two major organizations we must deeply collaborate are NASA and the NSF. Both of these organizations have numerous safety and environmental policies that we make sure to follow while conducting our mission. In any NASA mission, safety is their number one priority. So with our project, our employees will follow safety guidelines at all times. And as we are also conducting our mission from Antarctica, we also need to follow policies from the NSF. For example, we must use a benign bacteria in order to ensure the safety of Antarctica's wildlife if something goes wrong. And as previously stated, NSF requires that we must perform a safety test in New Mexico to make sure our systems work properly. And now I'll pass it off to Marissa.
Hello, my name is Marissa Solomio, and I'm from Virginia Beach, Virginia. I'm an applied scientist from the Science Office. For benefits and impacts on society, the data collected after our mission could help lead to NASA spinoffs to help the public health. In addition, our mission could find an improved way to protect astronauts from solar radiation and cosmic rays. This will also come into part with the future of space colonization to Mars and beyond. Finally, with the data collected, a way to make space travel more feasible is by protecting the spacecraft with magnetic shielding. And for the future of economic benefits, the rare earth magnet that our mission uses is more cost effective than an electromagnet. For instance, electromagnets use a lot more power to run on. In conclusion, the rare earth magnet is a good benefit for our mission.
Hello, my name is Olivia Judd. I'm from Manchester, Virginia, and I'm a public relations specialist for the Office of Communications. On the left-hand side of the slide, we have our mission patch. The Rampart represents the mission acronym, with Wallops Flight Facility being the facilitator for the Rampart mission. The scientific balloon and Earth demonstrate our mission platform, with the prokaryotic cell in the middle of our mission patch represents the subject of our mission. On this slide, we have sample social media posts that will be used to interact with the general public. What is posted on social media is dictated by what education events are occurring. Educational plans such as lectures, internships, and lessons plans will be shared on social media. The forms of social media used for the Rampart mission are Twitter and Instagram. Social media is utilized to post updates, live streams, photos, and videos to display the mission progress from start to finish. Social media will include more condensed and brief information to keep the public engaged in the Rampart mission from the start. Both social media sites will be updated once or twice a week to keep info up to date.
Hello, I'm Mariette Hollins from Charlottesville, Virginia, and I'm a public relations specialist from the Office of Communication. For my outreach program, elementary school students will have a lesson plan in which we discover magnets as well as balloons and eventually launch our own balloon into the sky. We will also take them to the Air and Space Museum in Washington, D.C. or a local science museum nearby. For middle schoolers, we have a more complex lesson in which we study bacteria as well as magnetic fields, preparing them for high school biology and physics. We will also help them to apply to Cubes in Space by iDoodle EDU Incorporated, in which they send their own experiment on a sounding rocket into space. For high school students and college students, we will have a lecture in which we discuss zero pressure balloons as well as environmental impacts of our mission. We will also have an internship in which we launch their own balloon and follow along with us on our mission. We will also help them to apply to the High Altitude Student Platform with NASA, in which they will send their own experiment into space on a balloon. For the public outreach, we have created a press release in which we discuss the mission as well as its impacts on society that include irradiation of a biological system, spin-off medical use, new work on DNA replication, and the future of space colonization. Thank you so much to Mr. Braun, Mr. Hamilton, Alana Dervin, our intern, and Miss Benner for our week here.
Okay, nice job, scientific balloon. So now we'll open it up for questions from our audience. Great presentation. I learned a lot about scientific balloons. How does the strength of the magnetic field of your rare earth element magnet compare to the strength of the Earth's magnetic field?
So that's a great question. So the Earth's magnetic field is actually very strong, but since it's spread out over a large area, and especially at the high altitudes that we're at, it's generally very weak. And a 1 Tesla magnetic field from a rare earth magnet is a very strong magnetic field, so it will dominate the Earth's magnetic field locally. But the magnetometer instrument will analyze the effect of the Earth's magnetic field as well, so we can account for its influence on the payloads, although it will probably be negligible.
Okay. Our next question is from Belinda Henriquez. Let's see, Henriques, sorry. Let me go back up. Excellent job. It was stated that your bacteria will grow, not too much. How will you control the not too much, especially, hold on, if retrieval would take up to 2 years?
Yeah, so we are launching our scientific balloon from Antarctica. This means that when the scientific balloon falls, the payload is going to parachute down into Antarctica. And based on the temperature that our bacteria grows at and the conditions for the bacteria, being in Antarctica is going to drop the bacteria into stasis, which means that it will stop reproducing, which will basically keep it still and not growing until we are ready to pick it up. And then we will keep it cold until we are ready to do analysis.
Okay, great answer. Our next question is great presentation, impressive education outreach plan. Do you have a goal of how many students you would like to reach?
Hi, yes, I can answer this question. We are looking for a class size of around 24 students for middle school and elementary school, and for high school students, the lecture will have around 100 students, hopefully.
Our next question is, are you concerned the magnets may adversely affect the sensitive electronics in your payload? If not, why?
So the type of magnet we're using, the rare earth magnet, is pretty strong. It has very strong. We're using the magnetic field requirement of 1 Tesla, which could possibly have adverse effects on the electronics in the payload. However, since the magnetic field shouldn't be moving a lot or turning on and off, these effects could probably be mitigated by distancing the magnet from sensitive electronics, and the effect would probably be negligible.
To add on to that, we will also be storing our data on solid state drives, which do not have hard drives, which do not have as much of problems with being close to magnets.
Okay, what instruments do you have to measure radiation? And if so, what types do they measure and how?
All right, so we have a couple different instruments for measuring different types of radiation. The first one is the energetic charge particle detector, which will measure the charge and energy of alpha and beta particles and protons, which are mainly from solar wind, and they're lighter particles. We also have a cosmic ray spectrometer, and cosmic rays are generally from deeper space, and they're a super energetic atomic nuclei that are stripped of their electrons. Really measuring the energy and type of these atomic nuclei with the cosmic ray spectrometer.
Okay, good answer. We have another question. This probably goes off of one of the questions that you've already answered. It says, great job. If for some reason you weren't able to recover your payload, will you still have means to collect your data?
So part of our mission is it's a remote analysis of the bacterial growth. So we have specialized instruments you're using in flight, which are relaying telemetry over satellite networks, so that we can monitor the bacterial growth to some extent during the actual flight of the balloon. And these include an optical turbidity spectrophotometer, which will measure the density of the bacteria, and the infrared thermography camera, which will measure the living bacteria based on metabolic heat, so we can determine how much bacteria are dying and how fast the living ones are growing. And we will also, if we are able to recover our payload, we will perform an Ames test, which will determine the amount of genetic mutation of the bacteria, which could have been caused by radiation.
In other words, could you have just done it in a lab?
So I can answer this question. There have been a few tests of magnetic protection of bacteria from radiation in a lab that has been done by Johns Hopkins and Rutherford Appleton, which is why we're partnering with them. However, it hasn't been done in space before, and so making the artificial radiation in a lab can be different from actual space, solar, and cosmic radiation. And so, because this has never been done in space, we are furthering knowledge about the topic.
Also, to elaborate on that, the testing that has been done has only been on using magnetic fields to deflect radiation, and none of them have analyzed their effects on bacteria. And so it's really important to determine how the bacteria will grow in a space environment with space radiation.
Great presentation and very interesting. We're going to move on now to our next group, and that will be Sounding Rockets 2.
Hi everyone, we are the Sounding Rockets 2 team and this is our mission Gaia, the Geomagnetic Auroral Induction Analysis. My name is Advitya Srinivasan, I am from Loudoun County, Virginia, and I'm the project manager as well as the research scientist of the Science Office for Sounding Rockets 2. This mission seeks to improve the understanding of the impact of geomagnetic storms on the thermosphere and to investigate the impact of the changing thermosphere on orbiting satellites in order to better understand the tendencies of auroras affecting satellites, telecommunications, and guidance systems orbiting the thermosphere. So we plan to launch a sounding rocket into the middle of an aurora to take measurements of the thermosphere using instruments from booms. We plan to measure various thermosphere properties such as pressure, temperature, and radioactivity. We also plan to launch a sounding rocket during the aurora and run around 90 minutes after the aurora as a control reading to see if there are long-term effects to the thermosphere. In the light of geomagnetic storms damaging effects on orbiting satellites, the data from this mission works toward more efficient protection and education against these adverse effects, which will benefit all of those involved, including the scientific community and the general public. Our main NASA goal is to discover, which means to expand human knowledge through new scientific discoveries. The main sub-goals that we are implementing are goals 1.1 and 1.2, which are to understand the Earth system and its climate, and to understand the Sun, solar system, and universe respectively. As part of our mission, we also have two different science goals and objectives that will lead us to each goal. Our first scientific goal is to study geomagnetic storms impacting the thermosphere. The objectives that will help us get to this goal are to number one, investigate the changing particle activity in the Earth's thermosphere, and number two, which is to take measurements of the thermosphere during and after these strong geomagnetic storms to see if there was truly a lasting effect on the thermosphere. Our second science goal is to investigate the impact of the changing thermosphere for orbiting satellites. The science goal is very important because it's the basis of our mission, as orbiting satellites are extremely important to everybody's lives, as these satellites may be from GPS companies, internet and phone providers, and the government and military as well. The objectives that will lead us to this goal are number one, satellite orbits could be impacted by the changes in the thermosphere, and number two, the data from this mission may lead us to other missions or studies in which we could calculate models or predict how the thermosphere will continue to be impacted or varied during our geomagnetic storms.
Okay, so my name is Christopher Lim. I'm from Fairfax, Virginia, and I'm the instrument specialist from the engineering office. As for our instruments, we will have four main instruments on our payload, three of which are the magnetometer, which we will use to measure electromagnetic fields and activity to just learn more about these fields produced by the geomagnetic storms and auroras. We use a barometer to measure air pressure, and a thermometer to measure temperature. And for our fourth instrument, we're using a sodium iodide scintillator, which we'll use to measure high energy radiation, such as X-rays or gamma rays. The reason we're using a sodium iodide crystal scintillator specifically is because it's relatively cheaper and it's more accessible than the alternative crystals. And this machine works by using a process known as scintillation, where the high energy radiation hits the sodium iodide crystal, creating a burst of light, which is then measured by the photoresistor. And as for how we're actually going to have some of the instruments in the payload, we're going to use something called booms, which are basically extendable metal arms with parts of payloads attached to them. And on these booms, we'll have the magnetometer, sodium iodide scintillator, thermometer, and barometer. And the reason why we're using booms is specifically for the magnetometer. Because it's such a sensitive instrument, we don't want the other electronics from the other instruments actually interfering with it, as we want to have accurate measurements of the electromagnetic fields.
My name is Teresa Varga. I am an instrument specialist from the engineering office, and I am from Fredericksburg, Virginia. So the other way we are going to be deploying our payload is through distributed payload communications. So we will have soda can size sub payloads, which will each contain a barometer and thermometer. They will be ejected from the main payload, and they will be able to collect data from multiple altitudes and locations simultaneously within the aurora that we are studying to allow us to get a much bigger picture of what the atmospheric conditions are like within the aurora. So we will have 4 of these sub-payloads, and they will be ejected at specific times between the 3rd and 4th stages of our sounding rocket. And then these sub-payloads will wirelessly transmit the data they collect back to the main payload, which will use its telemetry system to transmit the data back down to our scientists on Earth. As for the specific sounding rocket model we are going to be using the Black Brant 12A sounding rocket. So this is a 4-stage sounding rocket. The first stage is the Talos motor, the second is the Terrier, the third, the Black Brant, and the fourth, the Nika. So this sounding rocket typically carries payloads between 250 pounds to 1,050 pounds. And so just as an example, this sounding rocket model can carry a 1,000-pound payload to an altitude of about 500 kilometers, which works great for our mission because, I will explain on the next slide, we will have a payload of about 800 pounds, and we desire to get this payload up to an altitude of about 600 kilometers. And another reason that we chose this specific sounding rocket model is because this rocket has been used in the areas where the aurora borealis is normally visible and has been used on similar missions to ours. So here is the breakdown of our weight estimate. So as you can see, we currently estimate it at about 815 pounds. So we have on our table the booms, the sub-payloads, and all the instruments we're using, but as well as all the other devices that are necessary to a sounding rocket mission, such as the telemetry system, the altitude control system, and the water recovery system. And so here is the carpet plot for the specific model of sounding rocket that we are using, which helped us to come to the decision that this is the model that we need to use. So as you can see, the red circle kind of highlights the area where we desire to be because it has the range of our estimated payload weight as well as the 600-kilometer desired altitude. And the angles of the graph allow us, so if the aurora borealis isn't directly above our launch site, we are able to launch at an angle so that our sounding rocket is still able to record data from inside the aurora.
Hi, my name is Adair Poyer. I'm from Hanover, Virginia, and I'm the environmental scientist of the environmental. So on this slide, we have a flowchart of how the geomagnetic storms in the auroras further south are produced, and also how they impact satellites and the thermosphere. So it starts out with a solar max, which is when the poles and the sun begin to shift. So this produces more solar waves, which are full of radiation and a lot of electrons. So these solar waves hit their magnetic field and they disrupt and weaken it. And so this allows the electrons to enter the thermosphere. And so this causes a geomagnetic storm, which is basically just when magnetic field is disrupted. And so these electrons hit the ions already in the thermosphere and supercharge them. This causes them to release light, which is seen as the aurora borealis. And then this can cause the thermosphere to expand and others to change in it, which can thus impact the conditions that the satellites are moving through. Also, their orbits. As for legal and environmental considerations, we had to take a lot into account when planning this mission. One of our main concerns was our payload recovery, as we did choose to do water recovery as we are launching out of Hebride, Scotland, in order to reach the desired latitude coordinations. And so we had to make sure that the payloads were not damaged or damage anything in the water, such as aquatic life, and that all of the materials used would be safe in the water and be retrieved that way. So we had a water recovery system. key procedures for launch site safety, including launching beacons whenever the missile site was in use so that the public would know not to be closer, and as well as closing down roads on the day of the launch in order to make sure that the public would not be harmed by the launch itself. There were also a lot of launch considerations for the rocket, including emission limits that are set by NASA as well as wildlife impacts, seeing as there's lots of natural wildlife that is around the site and on the island that we are launching from.
Okay, so our operation timeline consists of around 18 months, which can vary from about a month or two more depending on the time that the geomagnetic storm itself occurs. It will begin with presenting the proposal concept to NASA at the Wallops Flight Facility, and once it has been approved, we will then begin putting the production of hardware and the instruments, which will then be integrated into the payload and tested before flight, which afterwards the payload will then be transported from the Wallops Flight Facility to Scotland for launch. After launch, we will then recover the rocket and analyze the data that is provided from the study. There are a lot of different reasons why the mission is important. One of these reasons are satellite malfunctions, which occur due to the thermospheric expansion, which will increase the drag, which not only will knock satellites off course, but can prevent them from reaching orbit altogether, which an example of this is in February of 2022, where the satellites were unable to make it into orbit and fell back to Earth and burned up within the atmosphere. Another reason will be power blackouts, which after an extended point in time will begin to shut off functions like water, perishable foods and medications will go bad, and there's a whole list of other reasons why the power is needed, and it's very important, especially because of the interconnected power grids, which will meaning that if power goes out in one state, it can spread to several others as on tandem.
Good morning. My name is Kamaya Wilson, and I'm from King George, Virginia. I am one of the public relations specialists from the Office of Communications. Here we have our mission stakeholders and partners. First up, we have internet and electrical companies. They have customers all over the globe and rely on their satellites to be functioning for their customers' use. Both NOAA and NASA currently have satellites in the thermosphere where we'll be gathering our data, so they will definitely benefit from the data we will be extracting from our mission. Next, the government and military. This is especially important as a lot of employees have been working from home, geopositioning companies, the International Space Station, as well as the general public who rely on them to get through their daily lives. As you can see here, this is our mission patch. As we all know, NASA likes to use mythological figures as names for missions as well as spacecraft. So my team and I wanted to follow along the same path. The name of our mission is Gaia, the geomagnetic auroral induction analysis. Gaia in Greek mythology was the personification of Mother Earth. In the patch, the trees are really the representation of Mother Earth, as when you think of the characteristics of Earth, you think of air, water, and trees. As our mission name is Gaia, I wanted to include a symbol of creation. There is the Aurora Borealis, since that is what we'll be studying. In our patch, you can see that there is a night sky. This is because we'll be launching at night to the early morning. There's also a sounding rocket trajectory in the middle. And then finally, our mission stakeholders, the NASA Wallops Flight Facility and NOAA, are at the bottom of the patch, as well as represented in these two stars next to the sounding rocket trajectory. We have several accounts across, we have several accounts across several social media platforms. Our Instagram will help us to reach our younger educators as well as a college-aged outreach group, as 63% of Instagram users are between the ages of 18 and 34. We also have a Snapchat.
Looks like they might be having some type of technical difficulty. Maybe another member of your team can talk about your part.
Okay. Hi, I'm Madison Shu from Manassas Park, Virginia, and I'm the other public relations specialist from the Office of Communication. In terms of our social media outreach, we also have a Twitter and Facebook page geared toward our older audiences. For our educational outreach program, we have created lesson plans for grades K through 12. Specifically for our elementary school students, we have a program where they paint the aurora borealis while their teacher explains our program as well as their needed curriculum. For our middle and high school students, we offer an art plus essay contest to advertise our mission and bring interest to the NASA's adolescent programs. Finally, for our undergraduate/graduate students, we have internship scholarship opportunities at NASA Wallace facility for research on the auroras. Prior to Gaia's launch, our public outreach strategies are set to release a fact sheet, website, and press release documentation sharing the importance of this mission to the general public. We also wanted to thank all these people for helping us with this mission and giving us the opportunity to research the auroras.
Okay, good job, Sounding Rockets 2. So now we have time to have a few questions. So if you have any questions. Okay, so we do have a question. We have, hold on, a lot of them coming in. All right, so excellent job. I saw the weight of your payload. I might have missed it, but what is the maximum weight that your sounding rocket can carry?
So our sounding rocket, the specific model we're using, the Black Brant 12, can carry payloads up to about 1,000 pounds.
Okay, and that you're just below that. So when I looked at your weight. So our next question says, nice presentation, Sounding Rockets 2. My question is, how long does it take for your payload to deploy? Will your sounding rocket itself impact the readings you take during the aurora?
Okay, so for the question for how long it takes for the payloads to deploy, I'm going to assume you mean the sub payloads. And in previous missions that use similar technology, they usually deploy it based on intervals that we calculate to determine the altitude, which are usually about a couple milliseconds, or not a couple milliseconds, but like 0.5 seconds after each launch. And they're launched in sets of 4, just to ensure that the balance of the rocket does not get thrown off balance, and as well as that it shouldn't impact the rocket itself, and the readings shouldn't impact them either, as we're launching them between the intervals of the 4th and 3rd motors being launched off, I guess, in a sense, so that the rocket is not accelerating during those moments.
Okay, the other part of the question is, will your sounding rocket itself affect the readings you take during the aurora?
Oh, I thought I answered that, but I might
Oh.
have missed that part. But it shouldn't actually affect any of the readings, as we're using mechanical springs to launch them away from the actual rocket itself.
Okay. All right, so our next question, it says, great job, Sounding Rockets 2. It is interesting to collect data from the aurora borealis. Can someone clarify the data you were hoping to collect? So specifically, what are you trying to collect?
So we don't have to look at the previous slide, but the specific things that we wish to collect is the temperature of the atmosphere as well as the atmospheric pressure, along with the radiation produced from the geomagnetic storms and the electromagnetic fields from the magnetometer. We're just going to use these things to see how the geomagnetic storm might affect Earth's own geomagnetic fields, as well as to see the radiation it produces and to see how the temperature and pressure are affected to see if there actually is an expansion of the thermosphere from these different types of auroras.
Great answer. All right, our next question is, what are your plans to make information about your mission available to those without internet access?
In order to reach those without internet access, we could also put information about our mission in newspapers as well as scientific magazines.
Okay. All right, so our last question will be, given that you were flying through the aurora, is wireless transmission of data a feasible option? Atmospheric plasma and other geomagnetic storm phenomena leads to high attenuation of signals.
So we have not yet done much research into the wireless data transmission, and we would have to look more into that. But in the case that the wireless transmission is messed up due to the effects of the aurora, all of the data would be stored on the hard drives within the sub payloads, so that when we do our water recovery, we would be able to collect all of the data from the physical payloads.
Okay. Thank you. Thank you for that great answer. All right, so we're going to move on to our next group, and that will be the small stats. Okay, small stats, are we having difficulties loading your presentation? Okay, so it looks like they're having a small technical issue sharing, and he says 1 moment. Small stats, we can move on to ELB if you want to have a few more minutes. Like he got kicked out. Okay, we're going to go ahead and move on to ELB while small stats gets their technical issues worked out. So ELB, if you could start with your presentation, that would be great.
Okay, we're started. Hello, everyone. My name is Rambir Alawalia. I am from Leesville, Virginia, and I'm the project manager and instrument specialist from the engineering office. Our mission at TRAMS is to test radiation with active magnetic shielding. Next slide, please. What we're going to do is use the Atari's rocket to launch a high Earth orbit. On the payload that we launch, we will have an electromagnetic field generator, which will be turned on and off to test active and passive shielding. We will have measuring instruments inside the testing capsule, which will measure how much radiation gets through both types of shielding, and we will compare our results to see how effective the magnetic shielding is. The strength of the magnetic field can also be adjusted so that we can adapt to future scientific needs for certain new missions that might require testing for radiation protection. Next slide, please.
Hi, I'm Advika Sampath Kumar. I'm from Loudoun County, Virginia. I'm the research scientist from the Science Office. Our mission aligns with 2 out of 4 of NASA's strategic goals, those which pertain to exploration and advancement. Deep space missions with longer timelines tend to expose astronauts and equipment to higher doses of radiation, which can negatively impact the astronauts' health as well as the functionality of the equipment. By testing technology which can better protect them from this exposure, TRAM supports NASA's goal to extend human presence to the moon and on towards Mars for sustainable long-term exploration, development, and utilization. This would also support objectives to safeguard explorers and enhance space access. In addition, by potentially improving protective measures, TRAMS also aims to enhance capabilities and operations to catalyze mission success, both for current missions as well as future missions, in order to fulfill the objective of transforming mission support capabilities for the next generation and era of aerospace. Next slide, please. The TRAMS mission science goal is to determine the ability of active magnetic shielding to reduce radiation exposure in a high Earth orbit. Our objectives work to fulfill this goal. We're trying to send prototypes of active magnetic shielding technology beyond the Van Allen belts into a high Earth orbit using the Antares launch vehicle. From there, we'll turn the shield on and off to collect data in order to quantify its radioprotective abilities. The data will then be evaluated by comparing radiation levels when the shield is active versus inactive, as well as compare the data to NASA's radiation safety limit for humans. Next slide, please.
Hi, my name is Ryan Yee. I'm from Fairfax, Virginia, and I'm a research scientist from the Science Office. So, the general space science community will benefit from this mission, since this is a real-life application of active magnetic shielding that, if it works, could protect astronauts from radiation-related health issues, such as cancer, and protect scientific equipment from failing on future missions to deeper space. The general public could also benefit as well, since this technology could be used on communication satellites to protect them from cosmic radiation. Spin-offs based on this technology could also be made for use by the general public. The Antares launch vehicle will be provided by Northrop Grumman, and it will be launched by NASA at the Wallops Flight Facility. Next slide, please.
Our active shielding will be generated with our electromagnetic field generator, or EMFG. The EMFG will generate a magnetic field around the testing capsule, which will repel the charged radiation particles in outer space. Most radiation particles in outer space that we will be dealing with, the most prevalent in space in general, are unstable positive nuclei, especially from solar flares. And magnetic fields can counter this. To accomplish this, a magnetic field will require at least 0.1 Tesla strength to operate properly against the other forces in space. This will require about 5 kilowatts of power supplied by our large solar panel, and it is also the heaviest and largest instrument on board. Next slide, please. Our primary measurement instrument is the Radiation Assessment Detector, or RAD. RAD was first used on the Curiosity rover, where it proved vital to the radiation studies done. The RAD is important because it identifies the type and energy level of the radiation particles. This is useful because we can identify which types of radiation the shielding is most effective against and how much energy the particles maintain if they make it through the shielding. It is both light at 1.2 kilograms and efficient at 4.2 watts, which is great because it saves space and power for the EMFG. Next slide, please. Next slide, please. Sorry, I don't see it switching slides. That might just be. Our secondary measurement instrument is a Geiger counter. And while the Geiger counter cannot measure the radiation type or energy level, it counts the ionization events, which are essentially the individual particles that pass through. Geiger counters are very reliable So this will serve as a redundancy to ensure mission success even if something else goes wrong. The power draw of the instrument is minimal and it weighs 1 to 2 kilograms depending on which model we would use. Next slide, please.
Hello, my name is Jonathan Hahn. I'm from Chantilly, Virginia, and I am the instrument specialist in the engineering office. Our platform will be the Antares rocket, and it is supplied by Northrop Grumman and will be launched from the Wallops Flight Facility. It will reach high Earth orbit, which for our mission will be about 50,000 kilometers above the Earth. Although our Antares rocket is originally a two-stage rocket, a modification is made for it for this mission, where there are now 3 stages arranged in a 2-3-2 configuration, which will give us the opportunity to reach high Earth orbit. Next slide, please. However, due to the extra stage, our payload capacity for this mission will be cut down from 8,000 kilograms to a maximum of 2,250 kilograms. However, our payload weight will be approximately 1,800 kilograms, which should be light enough to reach high Earth orbit. Most of the mass will be taken by the solar panels, which are required for the high energy demand of our instruments. Next slide, please. So for our operations timeline, so about 3 years before our planned launch date, we will submit our proposal and start developing our payload. About a year before launch, we will finish developing our payload and complete manufacturing. And a day before launch, we will bring the Antares to Pad 0A at Wallops Island. Next slide, please.
Hi, my name is Rolitza Venesian. I'm from Virginia Beach, Virginia, and I'm an applied scientist from the science office. For our post-launch timeline, we begin with the launch, and about 12 minutes later, the payload will reach its optimal position in the upper Earth orbit, will unfold and be ready for testing about 40 minutes in, and will start regular intervals of electromagnetic shielding impulses on day 3, continuing the cycle every 3 days until it's decommissioned at a minimum of 10 years. Next slide, please. Next slide, please. From a legal standpoint, it is crucial to first obtain an FAA expendable launch license and align our mission with national space policy, including NEPA and NFPA laws, ensuring protection of not only the people but also the environment on Earth. Next slide, please. Additionally, for the environment, our mission must follow the Endangered Species Act to conserve threatened and endangered species, such as the piping plover and the loggerhead turtle here on Virginia's eastern shore, and must follow international MOUs. Our mission also falls under the research encouraged by Donald J. Trump's executive order of 2019, which is to increase national resilience to electromagnetic pulses. Next slide, please. Again, in terms of environment, most impact comes from the ergomesh engine, which is a hybrid liquid oxygen refined petroleum engine, which, although is a relatively clean burning engine, still has some CO2 emissions. From the launch, there is also some environmental impacts, such as minimal sound pollution, addition to space debris as the payload will remain in space, and some NOx emissions from the on-ground generators. Next slide, please.
Hello, my name is Brooklyn Maciejewski. I'm from King George, Virginia, and I'm an applied scientist from the science office. The impacts of our mission will focus on improvements to our medical field towards the general public in oncology and occupational medicine, especially towards those who are exposed to high amounts of radiation. Additionally, our mission can serve to benefit the scientific community, as our data could be used to aid in the development of future space missions, such as the upcoming Mars mission in regards to radioprotective equipment and procedure, as well as resource protection. Next slide, please.
Hello, I'm Emma Music. I'm from Glade Spring, Virginia, and I'm the Public Relations Specialist from the Office of Communications. Here we have the mission logo. Starting outwards and working our way inwards, we have a thick outer gold border, which represents the sun. In the upper left-hand corner, we have our payload. If you look closely, we have, extending from the prongs, there's dashed lines, which represent the magnetic shielding which will be utilized in the mission. Further inwards, we have small stars, which represent people who have helped or directly worked on the mission.
For the brighter stars, the larger stars, we have corporations who have helped us along the way. The bright pink band in the middle, represents the Van Allen belts, and it is purple due to the radiation, to symbolize radiation. If you look closely, there's different shades of purple in the belt, which represents each department which has worked on this mission. Next slide, please. For our education outreach, we will utilize a virtual program which will be malleable to teachers' needs as well as available to students who do not use normal public schools. For K through 5, we will analyze our mission to a sunscreen and how astronauts need their own sunscreen in a sense. For 6 through 8, we'll have basic discussions on illnesses due to radiation. For 9 through 12, they will be able to come up with their own solutions to this issue. For college, they will have a moral rocket opportunity as well as internships. Next slide, please. For our public outreach, we will contact associations, including VAS, and we will also promote trams at conferences, which we will have interactive activities to help promote STEM as well. Next slide, please. For social media, we will use Instagram, Twitter, and Facebook. We can post photos as well as information about launch location viewing sites and progress. Next slide, please. We would like to extend a thank you to NASA and Walsh Flight Facility for making this program possible, as well as the Virginia Space Grant Consortium. And then we would also like to extend a very special thank you to Charles Younger for his help on this mission. Thank you for your time and consideration.
Okay. Great job, ELB. So what we're going to do now is we'll go to questions. So if you have any questions for ELB's mission presentation, please put them in the chat. I'll give you a minute to do that. Okay, great presentation, guys. My question is, how will you engage your mission stakeholders?
For our stakeholders, sorry, could you define what you mean by engage? To communicate with them or to get them involved?
I guess to let them know what's going on and get them involved.
So that will basically we will just stay in communication with them, and for our stakeholders such as Northrop Grumman and NASA and my extension Walsh Flight Facility, we will just communicate with them and work together to fit our payload with, for example, Northrop Grumman's rocket, and work with NASA to make sure the launch goes smoothly at Wallops. Does that answer your question?
You'll have to look in the chat. I think he's putting in answering. All right, our next. Yeah. So our next question is from our intern. What about shielding against energetic negatively charged electrons?
We didn't get that far into our research just yet, but that will require, we can change the testing, how we test with our magnetic fields on the payload, and we can try and target using information from the RAD to focus on those and see how we could best counter negatively charged particles as well as positively charged.
Okay. All right. Our next question comes from another intern. It says, great job. Would you be able to tell me what your pre-launch timeline looks like?
I believe we have already covered that in our presentation, but we can go over it again. So about 3 years before we actually launch, we submit our proposal and start working on our payload development. And then about a year before launch, we will complete our payload development, and we'll also complete our manufacturing. And about half a year before launch, we'll begin testing our equipment, and about 60 days before launch, we'll complete our testing, we'll complete our community outreach in anticipation for the launch, and about a day before, we'll bring our rocket to the pad. Oh, does that answer your question?
Can see, I'm sure it does. All right, so we're going to move on to the next question. It says your RAD instrument appears to have a small detection area. Have you considered how it will be placed to maximize data collection?
So for our payload, what we have is a separate instrument capsule where we will be doing the experiment, which is in a way isolated from the other aspects of the space payload for communications purposes. And what this idea is still in development, but what we were thinking about doing is having a kind of sensor array that lines the interior wall, in a sense, of the instrument capsule. And with that, with lots of sensors, we could essentially, from all angles, read the radiation and then funnel that back to the RAD for analysis. Does that answer your question?
I'm assuming so. I'm sure it did. Okay, so another question, it says, can you explain what NOx, N-O-X, stands for, why it may have a negative impact, and how you might mitigate those effects? Excellent work.
So NOx stands for nitrogen oxides, which are named NOx with the X standing as a placeholder for different ratios of nitrogen to oxygen, such as NO2 or NO3. And essentially, they're basically forms of smog or an air pollutant, which comes from most vehicle emissions and can deplete air quality. But we talked to environmental experts at Wallops about this, and she said that while there are some NOx emissions from the generator, since they do run in place of electricity on Wallops, it is relatively negligible, and it's not as big of a problem that we have to address it, at least not this case right now. Does that answer your question?
She'll probably put that in the chat, but I'm sure it did. Okay, so our last question, it says, great work, ELV. This is a really neat mission. Question, will the active shielding impact spacecraft communication?
So we noticed this problem, and our solution is we have the instrument capsule, as I said before, and right next to the instrument capsule, we have a very large solar panel where we get our power from. And on the back of the solar panel, which faces the instrument capsule, we will have a copper shielding layer, which should protect our comms, which will be on the other side of the solar panel, from all the impacts of the magnetic fields. Our comms will be placed in such a location where they don't impact the solar panel's output that much, but they will be shielded from the magnetic fields due to the copper backplate.
Okay.
Does that answer?
Looking at the list. Excellent answers was in your chat. Okay, so great job, ELV. Great job for the week. So we're going to go ahead and move on to our last group, which will be small stats.
Hello, my name is Nate Campion. I'm from Virginia Beach, Virginia, and I'm the project manager and the public relations specialist from the Office of Communications. Our mission is called the Asteroid Composition Collection and Evaluation Surveying Satellites, or ACCESS, and we intend to identify the composition of the 2019 AN27 asteroid. To do this, we will launch a constellation of 3 small satellites, one equipped with a 3D LiDAR, one equipped with a magnetometer, and one equipped with a gamma ray and neutron spectrometer. To transfer the data collected from these satellites to Earth, we will be utilizing an optical communication system. Once we have collected the necessary data, the satellites will collide with the asteroid. We will first send the satellite with a magnetometer, and the lidar will create a 3D model of the asteroid after the collision, which will show us the effect the collision had on the topography. And the spectrometer will check if there are any new materials, perhaps underneath the surface of the asteroid. Then, the satellite with the spectrometer will collide with the asteroid. Once again, the 3D lidar will create an updated map of the asteroid. Finally, the satellite equipped with the 3D lidar will collide. We are specifically measuring the debris pattern since this, in addition to the topography, will help us to determine where to land whenever we have the technology to mine asteroids.
Hello, everybody. My name is Jagdeep Pramadipatla. I'm a research scientist in the science office, and I'll essentially be going over the science goals for this mission. So from the lens of NASA, we're essentially going to be discovering, exploring, and advancing. Pursuing access will allow us to both discover and uncover the composition of these asteroids that we have in the asteroid belt. And pursuing access would also allow us to explore not only the asteroid belt and the area and the trajectories to get there, but it will also allow us to explore in an implied sense the rest of the universe as well, as pursuing access will allow us to support other NASA missions, such as the Artemis mission and other NASA missions that will take us to Mars and beyond, as we'll be able to fuel them through the information that we retrieve from these asteroids. We'll also be able to advance NASA not only in the sense of their information by researching the composition of these asteroids, but also through their technological suite, because we'll be essentially developing new optical communication, storage, and computation systems for use within this mission. So one of our primary goals is to support future NASA missions, and the specific mission that comes to mind is the Artemis mission, which will be taking us to Mars and beyond. And it's very difficult to retrieve elements and materials from Earth in order to fuel these missions. So by understanding the topographical measurements and elemental makeups of the AN-27 asteroid and potentially other asteroids in the asteroid belt, we might be able to use these materials to fuel other NASA missions. And so we'd essentially be taking the measurements and understand the composition of these asteroids to determine the potential utility of them for use in these missions going forward. Our second science goal is to determine the viability of optical communication systems, optical storage systems, and optical computation systems within deep space. So if you take a look at the diagram on the right-hand side of the slide, you'll see three square boxes, magnetometer, lidar, and spectrometer. Each of those represent one of our three small satellites. The information from those will be processed through an electro-optical processing chip, which will be etched onto a crystalline structure, which will then be downlinked to Earth using a laser system.
If somebody could please mute their mic, that would be great.
Hello, my name is Benjamin Rad, and I'm a research scientist in the science office. This is our traceability matrix. Our first science goal is to discover new methods to aid future refueling and resupplying missions on Mars and beyond. We will be using LiDAR to obtain a full topography of the asteroid before and after every impact. We will be using a spectrometer and a magnetometer to determine the chemical composition and core composition of the asteroid. Our second science goal is to determine the viability of new technology in deep space. We'll be using a laser system, software, and an optical multimeter to write, send, and compute data. We chose small satellites because that is the best platform to achieve our mission goal. We'll be collecting data on the asteroid belt, and small satellites can effectively collect data in deep space. For our experiment, we will have a constellation of 3 small satellites, which will all contribute to the data collection process. Since small satellites are inexpensive, new technologies and methods can be tested due to the easy repeatability. Our small satellites will be ride-sharing with Atlas V, and this will reduce the amount of materials that our mission expends. One constraint for our mission is the mass of the small satellites. Our satellites must each be under 150 kilograms in order to be categorized as small satellites. Another constraint is power. The satellites must not use more than 7 kilowatts of power in order to not use up all the energy produced by the solar cells. Our last constraint is time. Since our spectrometer is a gamma ray and neutron spectrometer, electromagnetic radiation from the sun disturbs the material and allows for the spectrometer to collect the elemental data. That means the data must be collected during the time frame where the asteroid is in the sun.
Hello, my name is Keegan Curl. I am from Fredericksburg, Virginia, and I am the instrumental specialist from the engineering office. For the small satellite mission instruments, we will be using a gamma ray and neutron spectrometer, which is a spectrometer that receives and reads the gamma rays and neutrons from its target and analyzes them to determine what element is present. It would be able to scan the whole asteroid throughout the course of its journey to identify the composition of the asteroid. In addition, we will be using an absolute magnetometer. It will be able to observe and determine the strength and orientation of the magnetic field throughout the asteroid. This is useful because the spectrometer can't penetrate far into the asteroid, so being able to detect the different magnetization strengths will aid in discerning the approximate percent composition of each element. The last scientific instrument we will need to accomplish the mission is the Kodiak 3D LiDAR. This instrument is an improved version of the time of flight 3D LiDAR and was specifically developed for small satellites by Goddard Space Flight Center. The satellites will have two main instrumentation devices on board the satellite. The ion thruster, which is a small yet powerful thruster used to propel the satellites through space. It works by taking inert gas, in this case xenon, and bombarding it with another particle, which will knock the electrons from the xenon out of their orbital shell. Then the positively charged ion is focused and shot out of the thruster. And the communication system, which will essentially be using a laser and polarization system. The system will emulate that of the DSOC used in the Psyche mission, but will also be paired with a 5D optical data storage system and a photonics-based processing system.
Hello, my name is Alex Abraham. I'm from McLean, Virginia, and I am the environmental scientist from the Environmental Office. The first part of this timeline is the mission proposal, where we propose the mission concept to the NASA scientists. Once approved, manufacturing will begin, and after 3 years, manufacturing and assembly will be completed. 13 months before the launch, the satellite will be delivered to our launch site, and 11 months before, we will power the satellite down and wait till launch. 210 days after the launch, the satellites will be ejected from the Atlas V rocket. This will be near where Mars orbits, and it will take 135 days after ejection to arrive at the target asteroids. 4 days after arrival, the satellites will begin data collection and send the data back to Earth. The next day, we will perform a controlled collision to gather data on the internals of the asteroids. If everything goes to plan, there will be no adverse effects on the environment. The satellite will only be powered on when it is deep space, so it shouldn't affect the environment of Earth. The only environmental effects would come from the failure at launch. If a failure occurred, the satellite would burn up, releasing harmful gases into the atmosphere. We can't change any of the functions of the Atlas V mission, but we are saving emissions by ride sharing. The mission would affect the target asteroid, but this would be for scientific research, and we would also gather the permits necessary to perform this collision. Some of the legal issues we will face is the handling of hazardous materials, the Endangered Species Act, and permits to make a controlled collision with an asteroid. The Department of Transportation requires that all hazardous materials that relate to the satellite must have precautions. So when transporting the satellite, we must follow these specific precautions. We also have to make efforts to conserve endangered species during launch. And lastly, we must get correct permits to perform a controlled collision with an asteroid. The data collected from this will benefit scientists at NASA and all over the country.
Hi, my name is Vincent Nguyen. I am from Richmond, Virginia, and I am an applied scientist from the Science Office. I help my team research the mission impacts such as economic and social ones. So let's start with the economic impacts first. So in the future, when Earth is running out of resources, stakeholders can determine the best asteroid to mine based on the asteroid's composition. They can then use this information given by NASA to help plan for future missions to mine those asteroids. The stakeholders of the mission include NASA, multinational corporations, and mining companies such as Deltian Innovations, Moon Express, and iSpace Incorporated. Asteroid mining can help these stakeholders profit from these resources when they resell them as goods to consumers. And another economic impact of asteroid mining is that the prices for these resources would drop because they would be abundant on our planet. So let's move on to societal impacts. So asteroid mining can reintroduce many new materials such as iron, steel, and aluminum, as well as minerals such as gold, platinum, and magnesium. So society will be supplied with abundant resources and will no longer need to worry about resource depletion on our planet. And the benefit of returning these extracted materials to our planet is the reduction of environmental impact. So people would no longer need to deforest, mine, and utilize the Earth's resources. So to reiterate, there are many benefits of asteroid mining, including the reduction of pollution and deforestation on our planet, the reduction in the cost of natural resources, and the ability to find abundant materials in space.
Hello, my name is Amelia Rizzo, and I am from Arlington, Virginia, and I am a public relations specialist from the Office of Communications. So on our mission patch, the gold border and gold mission name symbolize success and curiosity, which represents our mission because we are trying to discover what elements certain objects beyond Earth hold. Moving inward, our patch depicts Mars in the lower left corner because the data collected from our mission will likely be used to facilitate resupply missions for future Mars explorations. And finally, in the center of our patch is one of our small sats, which is shown surveying the asteroid 2019 and 27. As for public outreach, we have created a press release, which gives a general explanation of the ACCESS mission and will be published on multiple news sites. And additionally, we are planning on hosting a STEM convention to provide opportunities for people to not only learn about the ACCESS mission, but also to do experiments and hands-on activities that relate to it. And we also plan on hosting a satellite naming event where people will be able to submit name ideas for our 3 satellites and then vote on their favorites. And additionally, we plan to create a personality quiz that will assign people a satellite based on the answers they choose, which, like the naming event, will get people invested and will make them want to stay updated on the satellite they were assigned, because it forms a personal connection between the person who took the quiz and the satellite they got as a result. And finally, we plan to design a video simulation of our mission, which will allow people to visualize what our satellites will do and how they'll do it, and a video game where the player can control the satellites. And we also have both an Instagram and a Twitter page, which people can follow for more information and for updates on the ACCESS mission.
We also have plans for educational outreach as well. The elementary students can have an activity where they create their own asteroid belt. This will get the elementary schoolers excited about the asteroid belt and get them interested in the possibilities that are held there. Additionally, the middle school and high school students can have a speaker presentation where the speaker will be informing the students of the significance of our mission, a rock identification activity, which is an oversimplified version of what we're doing, where students will test several qualities of a rock and trying to identify what it is. And there will also be a teacher conference, because if we get the teachers interested, then they can also make their students interested. Finally, college students can have a science fair, which will get the students to experience what we're doing on a larger scale and on different scales in general. And they can be informed of the value of our mission by learning about it themselves, which is more meaningful to them if they learn about it from their own exploration. Finally, we would like to offer our sincere thanks to those who have helped us in our mission design, since this would not have been possible without this help from them.
We can open up for questions for our small stat mission presentation. So I'll give you a minute. Here we go. Excellent presentation. Is your goal, hold on, y'all coming in so fast. Is your goal to land on a specific asteroid? Also, can you explain what is meant by controlled collision?
So the goal for the asteroid that we're landing on is the 2019 and 27, and the controlled collision is essentially the satellite. Each satellite will it'll run into the asteroid. The satellites will be running into the asteroid, and we'll be using this to analyze the debris patterns, which will help us for if we want to land any vehicles on the asteroid in the future.
Okay, good answer. All right, next question. This is great mission concept, guys. My question is, what environmental impact techniques have been used for asteroid satellites in the past? Why did you choose the environmental impact mitigation strategies you did?
So I am not sure exactly what strategies have been used for environmentally, like making satellite missions environmentally friendly in the past. So I will research that. But choosing to ride share and only power on in deep space was meant so that we could have the least like environmental footprint on Earth, because by ride sharing we are utilizing a rocket that was already going into space to send missions instead of one, and by powering on in deep space we're not putting fuel into Earth's atmosphere.
All right. So another question is, have you considered any effects on data collection that solar storms such as CMEs have on your magnetometer readings?
As far as research had gone, we had into the magnetometer, we hadn't come across anything that rose concern, so we do not have any information on solar storms affecting the magnetometer.
Okay. All right. Our next question is it possible for your instruments to be damaged, destroyed due to these controlled collisions? What is your plan to collect data if this occurs?
All right.
So we have our communication system in place, our optical communication system, but the controlled collisions will be effectively destroying the satellite.
Yeah, so just to clarify that point a little bit, we're going to be taking the readings from the individual satellites themselves since it's a rendezvous. So they're going to be essentially orbiting the asteroid. So initially, we're going to be taking the measurements using the magnetometer, spectrometer, and LiDAR. And then once we take the magnetometer reading, since we won't really be requiring the instrument anymore, we'll be crashing that into the asteroid and then analyzing debris patterns. But this is after they downlink the data back to Earth.
Okay, any more questions? Let me scroll down some more and see. All right. Okay, I don't think there's any more questions. You must have done such an excellent job explaining your mission. So what we'll do now is thank you. Congratulations on a great job. Well done. And we'll move on through our program. Our next speaker will be our Deputy Director, Chris Carter, and he's going to give you a few remarks about our programs and our consortium.
Hello, Joyce. Can you hear me okay?
Yes, I can.
Okay, great.
I don't see you.
I do have my camera on.
See you now. We got you now.
Okay.
Okay.
Well, hello, everyone. My name is Chris Carter. I'm the Deputy Director of the Virginia Space Grant Consortium. Welcome to the closing ceremony of the Virginia Space Coast Scholars Program. Our director, Mary Sandy, regrets that she can't be with you today as she's leading the closing of one of our other programs. And of course, we would very much rather be having this ceremony at NASA Wallops Flight Facilities Visitor Center. It's a great place, but as you all know, we had to adjust our plans, and we were very disappointed to have to change the plans. But the situation does not take away from what sounds like a great academy. And this closing is just a celebration of a week's full of hard work. We were very excited and pleased to be able to offer this program as a residential event since we had to do the last 2 years of these academies fully virtually. But the Virginia Space Coast Scholars Program is the result of a vision that's shared by our director, Mary Sandy, and the Virginia Space Grant staff, and also NASA Wallops Flight Facility staff. Space Coast Scholars has been a fantastic program since 2013, with over 3,100 students participating, and almost 1,100 students have participated in the summer academies. Thanks to NASA Wallops for hosting this program and for the tremendous time and contributions of so many people who work on the program. And I especially want to thank Dr. Joyce Winterton, Linda Sherman, Victoria Dana, and Pat Benner for their tireless work in making Space Coast the success that it is. This NASA team has connected the students to some amazing NASA subject matter experts who contribute their time and knowledge in support of this program. Students and families, I hope you realize and appreciate just how special and unique this experience was. You just spent a week, well, nearly a whole week at a NASA facility developing a real life mission based on your research and interactions with NASA representatives. Very few students and people get to do this. Wallops is really a special place. Folks there do a great, inspiring work, and they are just wonderful people to work with. They really define what a great partnership is supposed to look like. Today culminates this wonderful journey for you scholars. You spent November through April in the distance learning program, and now you have where you learned STEM concepts through the focus on missions at Wallops. And throughout your coursework, you led by master teachers and interacted with your peers and studied material from NASA experts. And then students who did well in that course were invited to one of 3 one-week residential academy experiences at Wallops. And this is the last academy of the summer. More than 300 students from across the Commonwealth were selected to be in the online course. And then we had to down select to 120 students based on their course performance. So each of you truly earned your spot at this academy. We are committed to engaging students from throughout the Commonwealth, including students from areas that generally do not have access to these kinds of programs. We want to be sure that income is never a barrier to participate in space grant programs. So everything we do is free. I can't imagine how challenging and also exhilarating the week has been, not only for the students, but for the space grant staff and the subject matter experts and the mentors and the interns. The master teachers, you have been so working closely with your students. You are some of the best teachers in the state. You are represent the best of the best, and we appreciate your effort. Who else would take time out of the busy summer to keep on educating and working with students? They're always so energetic and perform with a smile. And I believe they are the real difference makers that separate this program and make it special. I hope you just enjoyed the amazing student presentations that were just delivered virtually. Fantastic work. They were presented so well by everyone. Thank you, students. I truly feel better about our future. Thanks to Rudo Kashiri, VSGC Education Programs Manager, who provides leadership and oversight of this program. A big thank you to Joyce Kubrick for her tireless work and coordination of Space Coast, and to Joyce Corriere, who supported the Academy on site, and Jan Dotzauer for her support as well. Thank you to our media specialist, Brian Williamson, who captured the students' experiences in video and still photography. You will see the fruits of his labor shortly. In addition to Space Coast Scholars, Virginia Space Grant also offers the Virginia Aerospace Science and Technology Scholars, or VAS program, for students in your junior and senior year. So that's the next step for you if you're interested. Similar to VAS is the Virginia Earth System Science course, or VES, also for juniors and seniors. This focuses on Earth System Science. Both of these programs have an online course and a summer academy hosted by NASA Langley, and students can earn 5 free college credits through Virginia Peninsula Community College. If you're interested in becoming a professional pilot, we have flight training programs, Pathways Flight Academies, and an online private pilot ground school will be offered this fall. You can learn more about these programs on our website. We also offer several scholarships, fellowships, internships, student spaceflight and design projects. So once you get on into college, you're still a member of the NASA and Virginia Space Grant pipeline. And we look forward to working with you to help you reach your goals. Parents, you can be very proud. If you see the work of the students, I think you've done a fantastic job. Really look forward to working with these students throughout our pipeline in the future. So thank you very much. Contact me anytime if you have any questions, and I'll turn it back over to Joyce.
All right. Thank you, Chris. So this week, it was a little challenging with the change sort of midway through, but the students, as you can see, still did an excellent job. I hope they had a great time, even with the changes that occurred. So, but this week would not have been possible, especially with the changes that have occurred, without the help of Victoria Dana, Patricia Benner, and Joyce Winterton from Wallops Flight Facility. I really thank you very much for your diligence in changing everything at the last minute and helping with the students, providing mentors and the tours that the students got to see. Also, I can't end this without thanking the master teachers and interns. The master teachers were just phenomenal this week and just really rose to the occasion when things had to change all of a sudden. They are just excellent people to work with, and your students are very fortunate to have them. They are Liz Petrie, Belinda Henriquez, Greg Dorsey, Angela Carter, Marina Whaley, and Nick Braun. So thank you again, guys and ladies. You actually were so helpful. And also our interns. The interns took time out of their summer to come and work with your students. These interns are very, very smart interns and have a lot to offer for your students' presentations as far as guidance and knowledge. So they would be Claire Kent, Julia Carter, Zachary Edicola, Zachary Valancourt, Alana Durin, Darren Upton, and Reed George. Really, thank you again for being so helpful and flexible in the time of change and still making it a great week for the students, for the teachers, for everybody. Okay, I really appreciate it. The students did an excellent job, as you can just see. So even though we had that glitch in our week, they still performed extremely well, and they worked together so well all week, either in person or online. It would be great to hear from all of the students, but we don't have time for that. So Samantha Ho, a student from this week's program, would like to say a few things about her experience this week. Samantha?
Hi guys. So participating in the Virginia Space Coast Scholars Summer Academy has been one of the most fun, challenging, and unique experiences that I've ever had. Within 1 week, we were able to get to know each other and work in our teams to research and gain knowledge in order to organize a mission using a platform related to the Wallops Flight Facility. In addition, it was also an amazing experience to witness other teams' mission achievements. Earlier this week, we were able to go on tours to the main base of Wallops Flight Facility, and we were able to learn about both science balloons, sounding rockets, and so much more. In addition, we were able to directly communicate and get advice from NASA experts on each of our platforms to help with our missions. Even though our time to be physically present at the Summer Academy was cut short, this program has really motivated me to learn more about space and even potentially pursue a career in this field. I've had so much fun this summer at the Academy, and I've gained lifelong friends from this program, and I'm sure I will keep in touch with them in the future. Thank you.
Thank you, Samantha. I hope everyone shares your sentiment and they all had a great time. Okay, so we're very fortunate to have Brian Williamson, our media specialist, there all week capturing pictures and video. He made several really nice videos, made a cute video for the students with the interns, a motivational video, but he also made a very nice closing video that sums up our week. You will be able to get this video and the pictures from the week. I will send you a link for our Flickr page so you can see the week's pictures as well as the closing video. And when I get the panel presentation video, I will give you a link for that as well. You can expect that in the next 2 weeks, maybe sooner. So I'll have that posted for you. Also, there is a program for this week, and that's posted on the students' it's a closing program on the student's course. So please have your student go on the course and download that if you'd like to have a copy of that for any future things you might need it for. Okay, so we're going to go ahead and show the video now, and thank you again for a great week.
go.
Hi, my name is Nate Campion.
My name is Kamaya Wilson.
My name is Luka Kalanchenko.
Hi, my name is Melissa Hovanesian.
Hi, I'm Carson Ray.
I've met a lot of really cool people. A lot of people here are very smart, very hardworking, and especially the people in my small satellite team, they're all very cool people and hard workers.
My team members are all very excited to be here. They're all very energetic, and I've just had a lot of fun with them. All of the mentors and teachers and interns have been so extremely helpful.
So I met a lot of friends here. They're really passionate, especially as I am. They're really smart people, and they did a lot of work to get here, and they're really great people and great students.
Everyone is so fun, and I really love my team. There's people who definitely have different strengths and different weaknesses, not really weaknesses, but strengths. And it works, our team, I think, is really well balanced. And a lot of people here are so knowledgeable about topics I hadn't even thought about. And I've been friends with some of these people for a while, and I didn't even know that they knew these things.
I feel like the master teachers and the interns are very helpful in designing the mission. We can ask them questions, but they let us do the work and come up with the ideas. And our subject matter expert is very knowledgeable in the topic, so I feel like we have a good resource.
It's really fun. I love the way they teach things. I love the way they give presentations and teach us how to present ourselves. And I love the way they teach us to have a mindset of a scientist and to constantly keep inquiring about things and to seek scientific answers to all of our problems.
Going in, I didn't really know what to expect because it was all virtual for a while, but so far I've loved it. Everyone here is so informed about what we're doing and so passionate about space and NASA, and it's really refreshing to see people aside from my friends who are not usually so interested in these topics.
I think it's been a really interesting program to sort of get in the environment of what a professional who's actually working on the NASA missions feels like.
Also, looking at the timeline of how long it takes to plan a mission was really interesting because it takes a lot more planning than people might think usually, which is kind of baffling to me.
I felt so excited. I felt like I was one step closer to my dreams. I was thinking one day I'll probably be behind this desk again, and probably I'll be the one being launched, and someone else is going to be sitting at that desk.
Joyce, are you there? Plan again.
Yeah, I'm trying, but I can't stop the video.
All right.
I didn't put it up. So I can't even, well, maybe I can mute it. Hold on. Let me try to mute it. Twice. Okay. Well, it was a great video. I wouldn't have mind seeing it again, but you know, we need to close up. So, thanks again for a fantastic summer. It was just great working with not only the students, but the master teachers and interns as well, and Wallops Flight Facility people. It was just a great week. Even though we had some little adversity, it really didn't stop our team. We still did an excellent job, and I'm very proud of everybody. So don't forget, scholars, to sign up for some of our other programs. If you look in the program that is on the course, the closing program, it actually has the links for BESS and BASS program for 11th and 12th graders. Remember that they also come with actual college credits if you choose to take that. They can start signing up for these programs in 10 days, August 15th. So don't forget to sign up if you're interested, and continue your journey towards the STEM career. Thanks again for this week, and hope you have a great summer.